Good afternoon, everyone, and thank you for joining this presentation. My name is Lana, and I will be discussing about liquefaction hazard modeling. This work has been done in collaboration with my colleague Anirudh, who has been a great support while expanding this capability in the OpenQuake engine. Similarly to what has been shown in previous talks, the results using scenario-based and the event-based calculators of OpenQuake will be presented. And note that the results are centered to hazard assessment only. Why should we consider ground failure now hazard and risk assessment studies? Contemporary seismic regulations require one to minimize the risk due to ground failure at the construction site. In saturated cohesionless medium, shear strength and stiffness decrease during earthquake due to the increase in pore water pressure. Earthquake loads are typically applied at the velocities that generate undrained conditions in granular material. Water in soil is incompressible, therefore any tendency in volume change will cause changes in pore water pressure and the effective stress. And as a consequence, this could give rise to substantial permanent ground deformation. One of the reasons why these analyses are not very common in our studies is that liquefaction is seen as a low contributor to the overall losses, and based on some studies, contribute up to 2.2% of direct losses. However, engineering community has witnessed remarkable examples of damage to infrastructure due to ground failure. And maybe two pivotal events are those that happened in 1964 in Japan and Alaska, where two large magnitude events caused significant damage to the built environment due to ground failure. However, liquefaction and severe consequences are not only related to the occurrence of large magnitude event, it can also be generated during moderate magnitude event, as we seen in Christchurch in 2011 in New Zealand. Liquefaction hazard assessment requires us answering several questions, and we start with whether soil is susceptible to liquefaction occurrence or not. If yes, what is the level of shaking, ground amplitude and duration that would lead to transition of soil state from solid to liquid? And if once liquefaction occurs, how severe the consequences are? Liquefaction is a localized phenomenon that does not occur everywhere, but it's rather limited to certain geological and hydrological settings where sedimentation process, age of deposition, water table depth, grain size distribution characterize the ground failure susceptibility of soils. And for example, we have the younger saturated sediments in coastal regions are very susceptible to liquefaction occurrence. Initial attempts to map the soil susceptibility to ground failure beyond the site scale dates back to 1978, when geological maps were generated, qualitative in nature, to delineate the region with higher susceptibility to liquefaction or ground failure in general. However, these kind of information are incomplete and they need to be supplemented with some quantitative data, like shown here, in order to produce the area of percentage of area that would be covered in liquefaction surface manifestation if an earthquake occurs. Loosely speaking, we group all the models for liquefaction assessment into three categories, and starting from middle, we have tier 2 or geotechnical models that are well established for site-specific and urban scale assessments, and they rely on the field test results and the empirical correlation. We refer to them also as semi-mechanistic models. On the right-hand side, we have fully mechanistic constitutive models that are using numerous model and soil parameters. These models are complex and expensive, and therefore we don't use them for everyday solving engineering problems. Our focus here is going to be on the least complex models on this spectrum, and those are tier 1 or geospatial models that are using variables with global coverage to characterize the soil wetness, density, and if we combine them with shaking, we can compute probability of liquefaction. These models are trained on the observed ground failures, thus they are merging the triggering component with liquefaction manifestation. And there are several of these variables that could be used as first-order proxies to characterize the density, saturation, and load. For saturation, we use typically groundwater table depth and distance to water bodies, wetness index, precipitation level. And for shaking, we use instantaneous ground motion intensity measures. However, more advanced intensity measures could be also explored. Peak ground acceleration is corrected by magnitude scaling factor to indirectly account for duration of shaking. Several studies have shown that peak ground velocity has stronger correlation with liquefaction occurrence, as ground motion with longer duration contains energy predominantly in longer period range. And out of these several variables that are available, we need to choose optimal ones to model our problem. And how do we do that? First of all, we need to have a solid understanding on the problem we are trying to model, and we can aid our selection using some statistical analysis. And in that sense, we are using Lucas and Cornell approach that is evaluating the ground motion intensity measures for the purposes of probabilistic seismic demand analysis. So in its original formulation, it is tailored for structural engineering problem, but it has been easily adapted for solving geotechnical earthquake engineering applications. And several metrics could be used to evaluate these proxies, and we rely here on the proficiency metric. When we are choosing the ground motion intensity measure to characterize the shaking level, we need also to make sure that the hazard computability requirements are met. These geospatial models are following several steps when we are developing them, and we start with collection of data or evidences where liquefaction occurred, and associating sites with the corresponding values of features to characterize the soil wetness, density, and level of shaking. This database is then supplemented with information where liquefaction did not occur. We select the optimal set of variables using statistical analysis, such as Lucas and Cornell approach, fit the model to our data, and explore several outputs, such as probability of liquefaction, binary output, or liquefaction spatial extent. And here we can see an example of evaluation of the model performance in terms of the residuals. And given that these type of models are approximate in nature, we can consider this variability here acceptable. Bangladesh is situated on top of 3 tectonic plates, Indian, Burma, and Eurasian, and is very prone to earthquake occurrences. It is a highly populated country where the rapid urbanization is coupled with poor construction practices. 80% of the landmass is covered by soft sediments, generating a potential for liquefaction occurrence. It is also characterized by heavy rainfall, given its location in a tropical monsoonal region. Therefore, these evoke the need for ground shaking and hazard assessment. As has been discussed before, 12 events are identified, which can help us understanding the consequences an earthquake can have on a region. And here I'm going to consider a single event that occurred in 1885 and ruptured the fault near the capital of Bangladesh. And using the scenario-based OpenQuake calculator, we can generate 1,000 correlated ground motion fields, propagating aleatory and epistemic uncertainty. For each realization of these ground motion fields, we compute the probability of liquefaction, and here we see the average probability of liquefaction, which is elevated in the epicentral region and closer to some major water bodies, and it diminishes as we go further away from an earthquake source. However, to have a more holistic representation of hazard and understand which events contribute to overall liquefaction potential with non-negligible probabilities, we need to conduct the event-based analysis. And the event-based analysis is conducted using the same logic tree structures, same seismic sources as it has been used for the ground shaking assessment. And our main output of this calculation is the annual rate of liquefaction occurrence, which increases as we go toward the northeast of a country in zones with elevated ground shaking hazard and precipitation levels. We can also see the road lengths exposed to different levels of perils shown here, and also in which first level administrative division the infrastructure is highly exposed to each of peril. Although considers as the secondary effect, liquefaction can make significant contribution to losses. It is usually conducted at the site-specific scale. However, with these new geospatial methodologies, we can conduct even the nationwide analysis. And this type of analysis can help us in identifying the areas with higher likelihood of occurrence, where more detailed studies could be conducted. And with this, I would like to conclude my presentation, to thank you for your attention, and I'm happy to answer any questions.